Thank you for the introduction. This is joint work with Michal Feldman, Vasilis Gkatzelis, and Nick Gravin. And I'm going to be talking a little bit about our paper, Bayesian and Randomized Clock Auctions. So I'll first give an introduction to clock auctions, what they are, how they work, and I'll try to convince you why we think they're such an important class of mechanisms to understand better, particularly in the EC community. And then I'll talk about a lower bound on the performance of any prior free deterministic clock auction that really motivates our work of studying clock auctions given access to priors or randomization. And then I'll move into the work from our paper itself and present the three auctions that we propose. These auctions gradually need less and less prior information access but to perform well, but to address this decrease in information need to grow increasingly more and more complex. But first, let's take a look at what a clock auction might look like. So imagine that you're working for an airline and you want to allocate the final seats on a flight. You have a set of families of different sizes, each who need a different number of seats to board the flight. So for example, the family on the bottom has 4 members, so they need 4 seats and can't be served by any fewer. Each of these families has a private value for being served, and the total social welfare from serving a set of families is just equal to the sum of the families you serve, or the sum of the values of the families you serve. So for example, if you were to serve the green and blue families, you'd get a social welfare of 1,050. And since social welfare is additive and all the valuations are non-negative, you'd ideally like to serve all of the families, but of course there's some feasibility constraint dictating the subsets of families we can simultaneously serve. So in this example, let's say there are 6 seats remaining on a flight, then there are the following sort of 3 maximal feasible sets you see here in brackets. And notably, this feasibility constraint is downward closed, so you could also serve any subset of these maximal sets. So our goal is then to truthfully elicit these values and thereby maximize the social welfare of the families we serve, subject to this capacity constraint. Right. And sort of the standard approach in the field of mechanism design is to run a sealed bid auction, wherein the participating bidders each submit their value directly to the auctioneer in the form of a bid, and the auctioneer uses these bids to make service and pricing decisions. And we say that an auction is strategy-proof if no bidder has any incentive to misreport their value when they report their bid, right? And there are indeed many strategy-proof sealed bid auctions in the theoretical literature on mechanism design, but in the empirical work on mechanism design, there's this recurring question over and over again of, is strategy-proofness really enough for an auction to be practical and for an auction to truthfully elicit the values of the participants? And very often the answer is no. Why? Well, there are still issues related to incentives, right? Because understanding that an auction is strategy-proof may require parsing a complex mathematical proof, which is unreasonable for many bidders in many real-world scenarios. Second, there are issues related to trust, because all of the bidders have to trust that the auctioneer is following the stated rules of the protocol, and that the auctioneer is correctly computing the pricing. And finally, there's issues related to privacy. Since all bidders have to report their true value to the auctioneer, bidders with particularly high value for service might be revealing sensitive information that could be protecting a windfall. So all of these issues really make sealed bid auctions not very appealing in many scenarios of interest. So we'd like to somehow change the auction format to address some of these concerns. An alternative format often used in practice, for example in the FCC spectrum reallocation auctions, is known as a clock auction. In a clock auction, all the bidders face a clock price that is going to weekly increase over time, and they can simply drop out whenever the price becomes too high. And then we serve the bidders who remain at the end of the auction at their most recently accepted clock price. So as an example, let's say the auctioneer starts with a reserve price of 100 for all bidders. These prices may raise uniformly, but need not do so. Because I want to emphasize, for those of you familiar with sort of literature on item pricing, these are not prices per item. This is price for being served. So since the bottom family requires the most number of seats on the flight, it probably makes sense to raise their clock faster than the smaller families. And at some point in the auction, the price offered to some bidder is going to become too high, right? You can see that happen for the yellow family here. But since these prices are monotonically increasing, the yellow family can say, well, I'm never going to be willing to ever accept a price offer in the future, so they can reject and permanently exit. And this process will continue until the remaining set of bidders is feasible, at which case we serve them at their most recently accepted price. So they're kind of a neat format, right? It's a little bit more restrictive than sealed bid, but why do we like clock auctions in this paper? Well, it's because they address all of the problems that we talked about before. Clock auctions offer many appealing properties that are just not satisfied by the standard sealed bid format. First, we have better incentives. Because clock auctions are not just strategy-proof, they're obviously strategy-proof. You simply compare the current price to your actual value and drop out whenever the price becomes too high. Obvious strategy-proofness, if you're not familiar, has been gaining a lot of recent interest in the EC community because it's a very robust notion of strategy-proofness, even in the presence of like cognitively bounded participants. Obvious strategy-proofness also directly implies weak group strategy-proofness, which means clock auctions are robust to coalitions of bidders. We also don't have trust issues anymore. The pricing scheme is totally transparent. They see their asking price in every round. And clock auctions are credible, which loosely means that the auctioneer has no incentive to deviate from the stated rules of the auction in order to gain more revenue. And finally, they offer privacy, particularly to the winners. They never reveal their true value to the auctioneer. They reveal the minimum amount of information they would need to in order to certify that they should win. And if you want this combination of properties, which I claim are really cool properties that I think we should know more about, you need to design a clock auction. These properties, actually subsets of these properties, are unique to the family of clock auctions. So we'd like clock auctions to perform really well in practice, but unfortunately, some very early work on clock auctions showed that, in the CS community, showed that if they're forced to be deterministic and have no access to priors, they can perform really poorly. So let's take a look at the instance just to get a sense of what we'll have to deal with. Duding et al. In 2014 proposed this really, really simple instance of this flight scenario that we had before, where we have L individual bidders who each want one seat on the flight, and one group bidder who have L people in total who need all L seats, right? So this is totally trivial, sort of algorithmically. You either serve the left bidders or the right bidder. If you want to serve the right bidder, you can serve no subset of the left, but you can serve all the left bidders simultaneously. So there's only two maximal feasible sets, right? It should be really trivial, but they show that the inapproximability actually grows with this kind of an instance as the number of bidders grows. And loosely speaking, you can see this because if the bidder on the right has a high value, we can't raise their price that high without losing them, right? That would be bad. However, if the bidders on the left have this sort of like harmonic shape, we never realize, or their value takes on this harmonic shape, we never realize their high total social welfare without causing them to drop out along the way, right? So you can imagine uniform pricing them if you have no access to priors is the best you can do. But this total prior-free assumption isn't really reasonable in most settings that clock auctions have been deployed, as I said, the spectrum reallocation auction. So we want to investigate the degree to which we can circumvent this lower bound given access to priors. And at least in this instance, you should be thinking, this should be easy. If we know the bidder distributions, there's only two maximal feasible sets, which means the maximum expectation is a 2 approximation to the expected max. So it's this kind of observation that we're going to leverage to try to do better. So let's take a look at the auctions we study in this paper. And just to give you a sense of our results, we propose auctions for 3 different information regimes. One where we have full distributional access, one where we only have access to the means of the distribution and what our target optimal welfare should be, and one when we have no access to priors at all. But these auctions need to grow more complex as we move down this chart. So when we have full priors, we offer only a single price to each bidder. When we have limited priors, we are still a deterministic auction, but it's uniform pricing, many rounds. And when we have no priors, it needs to be a really complicated randomized auction. But in each setting, our auctions obtain a log k approximation to the optimal social welfare, where k is the number of maximal feasible sets. And notice this is in stark contrast to prior-free deterministic, which has no bounded approximation in k. We'll start with our deterministic auctions. And just to give the setting formally, we have a set n of n bidders, a bidder I as valuation vi drawn from di, and these distributions are independent. We say that the expected social welfare is, as we expect, the sum of expected values of the bidders. And there's some feasibility constraint f that defines the collection of sets of bidders we can simultaneously serve. And we think about downward closed f here, which means that if a set S is contained in f, then any subset of S is also contained in F. And this is a really mild constraint, right? Captures many settings of interest, the knapsack auction, like this airline example we had before, and sort of combinatorial auctions that you can think of with single-minded, multi-minded bidders, that sort of thing. Since F is downward closed, it's uniquely defined by these K maximal sets, and this parameter K is what we're going to try to approximate as best as we can. This is going to be the parameter of interest. And our benchmark is going to be the expected maximum value social welfare set. So this is exactly the benchmark in the profit inequalities literature, if you're familiar. Notice that it's expected max, not max expectation. And then as sort of standard, we say that an auction will achieve an alpha approximation if it serves a set that's within an alpha factor of opt. So smaller values of alpha are good here. So for our first setting, let's assume we have access to the full distribution of each bidder. In other words, each bidder draws her value independently from a distribution we know. When we know the whole distribution, observe that we can infer almost any statistic we want. For example, the benchmark, we can infer the expected posterior value of a bidder, given that she accepts some price, and many others. And with full access to prior information, we can achieve much improved bounds even with a very simple class of clock auctions we call single price clock auctions. How do these work? They broadcast a single vector of prices, pi for each bidder I, observes the responses, and then selects a winning subset from among those who accept their offer. So to see an example, the values are private, the distributions are public in blue, and these are the disjoint maximal sets contained in the rectangles. So you post a price based on these distributions and the feasibility constraint. Bidders whose value exceed their price remain, and those who are lower will exit. There we go. And then you can choose to serve any subset of bidders from this point. So for example, maybe you serve the bottom right because it has the highest sum of accepted prices. Before I emphasize, and let me just emphasize, that kind of auction will give us a log K approximation. But I want to highlight a connection between single price clock auctions and sequential pricing mechanisms. Right? So we offer a single price to each bidder, which is sort of exactly what happens in sequential pricing and profit inequalities. In a sequential pricing mechanism, bidders are approached one by one, and they're offered take it or leave it prices. So the only difference between single price clock auctions and sequential pricing mechanisms is the ability to defer acceptance. In a profit inequality-based sequential pricing mechanism, if a bidder accepts their offer, you're forcing yourself to serve them. You're making a commitment to serve. Whereas in a single price clock auction, we observe all the responses and then choose who we want to serve. And as it turns out, this is really powerful because sequential pricing mechanisms, you can show, a series of papers have shown actually, that you can't hope to do better than a log K over log K approximation using any sequential pricing mechanism where K is the number of maximal feasible sets in a general downward close setting. On the other hand, sequential pricing mechanisms can rely on the responses of bidders that it's already offered to adapt its offers, whereas single price clock auctions offer simultaneously to everyone. So as it turns out, in this general downward close setting, deferred acceptance seems to be exponentially more powerful than adaptivity. And this is just actually what our clock auction looks like. And just to give you a sense of what this is, it's kind of complicated. There's this parameter delta that we can infer from the distributions. And we'll offer one of log K different prices, particularly the one with the highest expected welfare, that's either offering everyone a price of 0 and just relying on expectations, or this scaled value of delta. And you should be thinking about these prices as p equals 0 as a low uniform price. So no one's going to reject. But the people who accept, we don't really learn anything. On the other hand, we could offer a high uniform price, which this delta is a very, very high parameter, but we'll lose possibly many bidders. However, those who accept, we update their posterior, and we know they live in the tail of their distribution, and therefore we can get a lot of expected value from them. And that's sort of how we prove it, is we decompose the benchmark into two cases. Small sets of bidders that contribute at least half, we want to get those by offering high prices. Whereas if only large feasible sets of bidders contribute at least half of the welfare, we offer a low uniform price, this p equals 0. So now I'm going to turn quickly to the limited information setting. which is sort of in the literature on parametric auctions. And by slightly complicating our auction format, we can slightly relax our prior assumption and assume we only need the expected value of each bidder and the benchmark. So how do we do this? Well, if we don't have the distribution, we can't compute that delta. So we need to do something more. We need to leverage clock auctions. And we're going to leverage the ability to offer more than one price. We're going to sweep over uniform prices to gradually discover a price that's going to get close to the benchmark guarantee. And this is just sort of stating it a little bit more formally. It's essentially that there's a uniform price ascending clock auction that achieves the same log k approximation, only given access to these two parameters. And finally, in the last sort of minute, I'll give you a preview of this prior free clock auction. Remember that now we need randomization. Deterministic prior free clock auctions can't hope to get anything. And we re-examine this previously proposed auction of Christodoulou et al. Called the Hedging Auction, which is a clock auction. And we basically just provide a tighter analysis of this auction using our analytical tools that we develop in this paper. We get the same result. We get the exact same log k approximation to the optimal social welfare for any downward closed feasibility constraint without any prior information by just running their hedging auction completely unedited out of the box. So I'll just conclude with some interesting questions. First is, what is the best approximation that you can achieve with a clock auction? I think this is a really natural and well-motivated question, particularly in well-motivated structured combinatorial settings like matching, knapsack, or single-minded bidders. What is the power of this limited clock auction? So if you have to bound the number of rounds of interaction, what can you sort of get? This is sort of related to a presentation of Rod yesterday on this batched profit inequalities. And sort of what's the comparison in power of deferred acceptance versus adaptivity in simple settings? And finally, I just think clock auctions are really understudied in general, and they're a really fascinating and important class of mechanisms that have a lot of theoretical depth and practical importance. So you can pick your favorite setting of interest and just sort of study them more, and I hope more people work on these important mechanisms. That's all I have. Thank you.
Thank you very much. So we have time for a few questions while maybe the second speaker can already set up. Any questions from the audience? Yes?
Do you know, are any of the results you have tight, or is any aspect of the analysis tight?
Excellent question. So we have some in-progress work. The bounds are certainly not tight. I'll say that much. Open question, maybe even a constant for general downward closed. But we have unpublished sort of in-progress work that basically shows that you need to use discriminatory pricing, even if agents look totally symmetric, if you want to do better than like log n or log k.
And the follow-up question is, if all I tell you about a setting is the parameter k, but I don't tell you anything about the distribution, is there any reason to expect that some set systems with the same parameter k would be easier or harder than others? Or do you think, like, if the distribution should be worst case, then k really captures how hard it is?
Excellent, yeah. So one of the sort of drawbacks of our work is this parameter k, which is sort of clear to see that like in an n over 2 uniform matroid, this is exponential. But clearly in an n over 2 uniform matroid, clock auctions are optimal with no access to priors. You just run uniform price and choose the top n over 2. So k is not exactly the right parameter necessarily. It just happens to be one that captures any downward closed setting. You could imagine, for example, the number of matroids in intersection required to most succinctly describe the setting could also be an interesting parameter, and that's wide open. Mm-hmm.
In the final setting, where you only know the mean of the distribution, do you have any intuition of what would change if you know a confidence interval around the mean?
Great question. If you only know a confidence in... So I suspect that you can get similar results to go through just by sort of concentration type arguments. So if the set's large enough, then if you have a confidence interval around the mean, then you should expect that the sum of the values is going to concentrate pretty well. But no, I'm not 100% sure.